Hello and good morning from Indianapolis. Today is the third day of and the final day of our conference, Artificial Intelligence Applying Research and Engineering Solutions for Emergent Needs in Healthcare, hosted by the Regenstrief Institute and the Indiana Clinical and Translational Science Institute. I would like to, my name is Eneida Mendonca and I'm Vice President for Research Development at the Regenstrief Institute. I also would like to introduce you to two colleagues that co-host of this conference. And that's Dr. Peter N.B., which is our CIO and president for the Regenstrief Institute, and Dr. Sean Granis, who is vice president for data and analytics at the Regenstrief Institute. Joining us today are 423 colleagues, all of you who have registered and represent about 14 different countries. I want to go over a little bit about the logistics for the day. For some of you who were in the previous days, we already know some of what I'm going to talk, but make sure that you see on the bottom right of your screen a Q&A button. This button should be used for you to ask questions at the end. The moderator will, which is today is going to be Dr. Umberto Tacchinardi, will be looking into that Q&A button to ask your questions to the presenters. Participants will have their videos and their audio off for the entire time. If you have any questions that you'd like to endorse, you can bring them to the front of the queue. Just click on the thumbs up at the icon on the QA, at the QA screen. We are reminding everybody to ask questions. We will try to go over all of them. If possible, the moderator may combine some of those in order to allow more questions to be answered, but we will try to go over all of them. I will now pass the baton to Dr. Umberto Tacchinardi, who is our Chief Informatics Officer for Regenstrief Institute, and he will introduce you to the keynote and run the panel that goes after. Thank you.
Well, good morning, everyone. As Dr. Mendonca said, my name is Umberto Tacchinardi, and I am the Chief Information Officer for the Regenstrief Institute. And I'm a proud member of the Regenstrief Institute community. I need to remind everyone or tell everyone that this is our fifth anniversary. It's a long story and tradition. This is where we would love to be hosting you in ideal situation. But we will make our best here over Zoom. Remembering everyone that Regenstrief Institute was, started with a very generous and very forward-thinking idea of the Regenstrief family, mostly Regenstrief himself, that used his experience as an engineer producing washing machines, and this is what you see in the entrance of our building. The ingenuity, he wanted to transfer that ingenuity to healthcare and produce goods for everyone. So this is a place to identify, invent, and implement. We have a number of faculty, investigators. It's a long tradition, as I mentioned before. There is a big footprint on research, and we also do business development, which is a very interesting characteristic of our institute. You probably heard about some of our flagship programs like LOINC and the internet, the Open MRS and Open HIE, which are very popular around the world. So with no further ado, I will introduce my good friend, Marco Antonio Gutierrez. He's from the Informatics Division of the Heart Institute, University of São Paulo Medical School. In Brazil, Dr. Gutierrez's research focuses on the application of machine learning to segment and classify biomedical signals and medical images. He was elected by the Brazilian Computer Society as senior researcher in computing applied to health. He holds bachelor's and PhD degrees in electrical engineering and computer science from University of São Paulo, completed postdoctoral training at the University of Southern California, and he will be joining this panel following his address. I want to highlight that Marco is today in a super stressful day. His hospital is part of a big compound of hospitals in São Paulo, in the city of São Paulo. And up to yesterday, it was a COVID-free designated hospital. And yesterday they changed, given overflow in other surrounding hospitals, to a COVID hospital also. So they are in a very, very stressful time, big hardship. And I thank you so much, Marco, for being with us today, even when you're facing those hardships. Thank you and welcome.
Thank you, Dr. Humberto, for the introduction, and thank you, Dr. Mendonca, to invite me for this talk today. It's a pleasure and an honor to be here. My talk is about artificial intelligence for COVID-19 outbreak screening. I will start for this talk with some concepts about artificial intelligence. Artificial intelligence is a subfield of computer science, or AI is any machine that simulates aspects of learning or any other feature of human intelligence. AI is a theory and development of computer systems able to perform tasks normally requiring human intelligence. Or you can define AI as any system able to pass the Turing test. What is machine learning, or ML? It's a field of study that gives computer the ability to learn without being explicitly programmed. It's a study of algorithms that improve their performance P at some task T with experience E, as we have well-defined task P, T, and E. What is deep learning, or DL? DL methods are machine learning methods based on learning data representations. They are usually related to the training of neural networks with many layers. This area has fast advances during the last decade, basically related to the big data boom and the cheap GPU hardware. The first developed as an applied, then as a theoretical field. AI has many subfields: expert system, machine learning, robotics, natural language processing, machine vision, and speech recognition. In machine learning, you can split in deep learning, in supervised learning, and not supervised learning. All science in AI is based on a mathematical model for a neuron. A typical neuron cell has a dendrite, a nucleus, an axon, and an axon terminal. You can model this neuron mathematically using the perceptron model proposed by Rosenblatt in 1957. You have many entries, x1 to xn, and for each entry you have a weight, and after that you have a linear combination of the entries, and the output of this linear combination is passed through a nonlinear activation function to get the results. You can put this perceptron model in a network with many layers. And just for comparison, the human brain has 10 power of 11 neurons, or 100 billion neurons connected in a network. If you have a simple neuron in a single layer, you have limited type of decision regions. And of course, you can't distinguish many things or objects or features in an image or in a set of data. If you improve the structure to, let's say, 3 layers, you can have the ability to identify different structures. In fact, the perceptron is connected in a multi-layer, for instance, for image processing. In this architecture, you have many layers, many hidden layers, and functions such as sigmoid functions to do the nonlinear part of the neuron. In this example, you have a single binary image with 16 by 16 pixels. And if you wanted to detect in such an image letters from A to Z, you have to connect 256 neurons in an input layer. You have to have a hidden layer with 100 of nodes, and in the output layer, you need to have 26 nodes to detect what appears on that image. The problem with this architecture is the number of parameters that you have to control. In these simple examples, you have 2005 weights in the first layer and 2,600 weights on the last layer. So if you compute the number of parameters, you reach 20,000 parameters to control this network and to obtain the image that is presented as input. There are another drawbacks in this architecture. This architecture is little or no invariance to shifting, scaling, and any other forms of distortion. In this example, if you move, let's say 1 pixel left the A, you activate different neurons. And if you move 2 shifts left the image, you activate 154 neurons. So it's impracticable. Of course, this causes problems in scale and other forms of distortion. You can't detect the letter properly using this kind of architecture. Another problem is that the topology of the input data is completely ignored, especially working with raw data. So you can't use this for image processing. And if we improve the resolution of the image, in this case, we are using a binary image. If you decided to have a grayscale image, the complexity of the network makes the problem infeasible. So the solution for this was the advent of convolution neural networks. Convolution neural networks are neurobiologically motivated by the finds of locally sensitive and orientation selective nerve cells in the visual cortex. A network structure that implicitly extracts relevant features. CNN are a special kind of multi-layer neural networks. CNN are inspired in the visual cortex that has a hierarchical processing. The image, after formed in the retina, is sent to a region in the cortex named V1. In that region, simple visual forms such as edges and corners are detected. After that, the information is sent to the V2 region, where intermediate forms, features, group of forms are detected. And finally, the information is sent to the V4 region, where high-level objects, descriptions such as faces, objects are detected. CNN are inspired in this kind of processing. CNN is a feed-forward network that can extract topological property from an image. Like almost every other neural networks, they are trained with a version of the back propagation algorithm. Convolutional neural networks are designed to recognize visual patterns direct from pixels images with minimal processing. They can recognize patterns with extreme variability, such as handwritten characters. If you compare traditional classification methods versus CNN, in a classification method, you have the input, you need to pre-processing the data for feature extraction, and after that, the features extracted are sent to a classification step to get the output. In a convolutional neural network, you have the input, the feature extraction is performed by the network. This feature extraction is completely shift distortion invariant, and the result you send to a classification to get the output. CNN architecture is formed by many layers and blocks of layers. The principal block is the convolution layer, where the feature extraction occurs. So we have the input image, send the image to a set of feature maps that extract features from the image. After that, a second layer, named the subsample layer, do the shift and distortion invariance, reduce the order of the image to get the principal features in such image. After that, there is another set of a convolution layer and a subsampling layer, and the final step is a fully connected layer that is sent to a classifier. Returning to our example, the 16 by 16 image, binary image, in the convolution layer where you have the feature maps. In this example, we have different maps, feature maps that are convolved with the image to signalize the neuron. This is performed using the convolution method. So you have the feature map applying to the image and resulting in a new image that is the convolution of the feature map with the image. This is done with all maps in the convolution layer. So this feature extraction, all neurons in a feature share the same weights. In this way, all neurons detect the same feature at different positions in the input image. This reduces the number of free parameters a problem that we posed in the beginning of this presentation. So, if a neuron in the feature map fires, this corresponds a match with the template. So in this case, this feature map activate many neurons in that image. The second step is the subsampling layer that you name the pooling. The subsampling layer reduces the spatial resolution of each feature map. By reducing the spatial resolution of the feature map, a certain degree of shift and distortion variance is achieved. In this example, we are reducing the feature extracted in the convolution layer, but you can observe that this reduction, you can understand that is the letter A. So the two phases, convolution and subsampling, are put together. And in this example, you can see that the result of the convolution is presented to the subsampling layer. And in this subsampling layer, you reduce the resolution by applying max pooling or average pooling. You decide for a group, for instance, for a group of 4 pixels, who is the pixel with the max value, or who is the pixel that represents the average pixel in that region. So you reduce, in this case, an image 4x4 in an image 2x2 with a max pooling or average pooling. The other step in convolutional neural network is an algorithm that we name backpropagation. Convolutional neural network are trained using this algorithm. Initially, the weights or the feature maps are choose using randomly selected weights. The calculate output for every neuron from the input layer to the hidden layers to the output layer is done using the perceptron. The result of this operation, we can measure the error of the detection with the desired output. The value of this error is used to update the weights and turns the process again. Change the weights, do the processing, calculate the error, do it again up to reach the minimum error in your system. So this process that we name it training takes a lot of time and spend most of the computational resources to be done. As an example, in the beginning of the 90s, the first CNN network named LeNet, due to LeCun that proposed this network, was used to process handwrite numbers. So this architecture proposed by LeCun is formed by 3 convolution layers, C1, C3, and C5, with feature maps of 5x5, 2 subsampling layers, S2 and S4, that reduce the dimension of the image by a factor of 2, and a fully connected layer that has a sigmoid activation function that is sent to a classifier. This is the LeNet working. You can see the numbers appears on the screen, and on the left, the information that is collected in each layer. As you can see, the last layer appears like a barcode. You have the signature of the number that appears on the screen. In this kind of architecture, we have 187,000 connections and about 14,000 trainable weights. Another interesting solution that we can obtain using convolution neural networks is the ability to maintain the characteristic of the image independent of the distortion, rotation, scaling. As you can see, the image is changed on the screen, but the detection is the same. The network detects the same number. So this hierarchical representation we name deep learning, and it is deep if it has more than one layer of nonlinear feature transformation. If your problem involves to detect face, in the first layer, you obtain patterns of local contrast. In the middle level feature, you obtain parts of the face, and in the high level feature, you obtain the face and send this to a trainable classifier. In the same way that our visual cortex works. You can use this concept in image recognition, but you can also use in text to select char, word groups, calls, sentence, story, or in signal like speech, sample, spectral band, sound, phoneme, and word. If you decide to use deep learning in NLP, the process is quite similar of the process I presented using image. You have a sentence and you try to obtain the principal characteristics in this sentence, and in the final, you can send the information to a classifier. AI applied in healthcare. AI is a powerful tool and a partner, as presented by the American Medical Association. AI can help humans to unlock the power of big data and gain insight into patients. AI supports evidence-based decision-making, improving quality, safety, and efficiency. Can coordinate care and foster communication, improve patient experience and outcomes, and deliver value and reduce costs, and improve health system performance and optimization. AI-powered automation is a balance between improving effectiveness and AI-powered automation. In one side, you have the quality, experience, outcomes, safety, ways to ensure patient safety, efficiency, usability, productivity, access to care, controlling costs. And on the other side, you have machine learning, supervised learning, unsupervised learning, reinforcement learning, natural language processing, AI voice technology, medical robotics. So you need to put in a balance where AI can help your health organization. In terms of supervised learning, most of AI success in healthcare are achieved through supervised learning. It identifies and underlying structured partners of data and trying to map input variables into discrete categories. It can be a data-driven clinical decision support to diagnostic analysis using medical imaging like CT scan, X-ray, MRI procedures, making medical diagnosis based on the symptoms, designing and selecting treatments based on biomarkers or other attributes, or identify at-risk groups based on health-related factors and social determinants. You can see supervised learning as a classification problem in terms of identify different types of disease. An example of this is the CHE Expert project. It's a large data set of chest X-rays and a competition for automated chest X-ray interpretation launched in 2019 by Stanford University. In this project, they have more than 224,000 chest radiographic images from more than 65,000 patients. The idea of this project is to identify phenotypes on the images automatically. The last challenge proved that the method proposed in this data set reached the area under the curve of 0.93. That is much so good. So the problem here is to automatically detect the phenotypes using neural networks. In the COVID area, this effort evolved to CT exams. So the idea is to extract visual features from chest CT exams for the detection of COVID-19, community-acquired pneumonia, or CAP, and other non-pneumonia. The base for this initiative is a data set with 4,000 CT exams and a network, a convolution neural network architecture was proposed to detect COVID in such images. They used ResNet 50, a kind of CNN. They used 90% of the data set for training and 10% for test. The authors achieved also very good results with 0.96% or 96% of the area under the curve. So in the right image, you can see the detection of COVID or COVID regions or features in that image that indicates COVID. At our group, we decided to distinguish COVID in chest X-ray exams. Chest CT is the gold standard for image modality for detect COVID, but chest CT is not available in some health centers in comparison with X-ray, especially in low-income countries. Our initiative is to detect COVID just using X-ray images. So we proposed a method based on an architecture of CNN named the UNet that has two parts, an encoder and a decoder. It's a sandwich of convolution layers, pooling layers, as I presented before. And this network detects or segment the lungs on the X-ray. And after that, the network detects features in that image. These features are sent to other information with the patient. And finally, we detect the presence of COVID in the image. So to test this architecture, we use the 3 data sets. The first one has 29 patients with COVID provided by the Italian Society of Medical and Interventional Radiology. The second data set has 127 cases of pneumonia non-related to COVID. obtained from the Spanish chest XR cohort, named the PED chest. And the third data set is a 39 patients with pneumonia non-related to COVID from the National Library of Medicine. These three data sets were used to train our network to identify the features or the most significant features in the image. We use as a validation 32 patients around the world collected from University of Montreal. And after that, we reach 51 mutual features that can identify the COVID-19 in the chest X-ray. So in this image, you can see the COVID detection in a CT exam of the same patient and the detection region of COVID in the chest X-ray. The method that we propose up to now has a performance, the area under the curve of 0.86. We are not satisfied with this performance. We are improved the method. And one of the problems is the number of images that we use to calibrate or to training our method. If you improve the number of images, you can improve the performance of the method. Here we have a summary of the AI methods for COVID-19 diagnosis using radiology images. We collected 6 initiatives recently published with different numbers in terms of images and patients. Also different approaches using CT exams, X-ray exams, and different AI methods, different architectures using CNNs. And also you can see different performances. Different performance in terms of area under the curve, in terms of sensitivity, specificity, and accuracy. So it's very difficult to compare different methods applied in different data sets and with different performances measured. So this is one of the main problems in convolutional neural networks applied especially in medical image, that involves to have a data set that is used for many developers, many scientists, and that the results can be compared. You can analyze supervised learning as a regression problem. In this case, the intention is to predict results with a continuous output. You can predict inpatient mortality and long length of stay based on EHR big data, predicting the number of emergency room patients during a specific period, need staff and beds based on past data, predicting patients' survival rate based on health conditions, age, and other characteristics. In this paper, they published an AI hybrid model to predict COVID-19. They combined the improved susceptible infected model, a model to detect the spread of the disease, combining this with natural language processing model and a long short-term memory network. It's a special kind of convolutional neural network that is sensitive to time series, temporal time series. And the intention here is combine these different technologies to detect or to improve the detection of the spread of the disease. So they published this recently, And in this example, the three methods look the temporal time series, and the network, the convolutional neural network, try to extract features from this time series, and all the information collected by the ISI model, LSTM model, and NLP model are put together. And on the right, on that table, you can see that the error, when you compare the prediction of the model, let's say the prediction of the regular model, the ISI model, with the ground truth, the mean error along this time series is 1.62%. And when you include the neural network and the NLP model, you reduce the error to 0.52%. Another initiative is to try to estimate the risk for COVID from meta-analysis of symptoms and conditions. At our group, we collect descriptive statistics of population groups from Singapore ILI study that report cases involving H1N1, seasonal influenza, and influenza negative, and the Shanghai meta-analysis of patients with COVID-19, 30 retrospective observation studies involved in this meta-analysis that classifying patients according to the symptoms in COVID-19 severe and non-severe. Using this information, we develop a neural network that can, based on the statistics of the symptoms reported in the meta-analysis, determine the weight for each symptoms. The network do a multinomial logistic regression, and the results of this network are the weights for each symptoms, like fever, cough, fatigue, and condition of the patient, like cardiovascular disease, CVD. We put this all together, and we propose a COVID-duc. It's a risk score based on the symptoms of the individual, and we apply this at our institution. And we selected the score above 3 as a probably condition that reports COVID on the individual. We use this to try to identify in our institution individuals with probably COVID positive. Individuals with COVID-duc above 3 are sent to the physician to analyze it, to do the test, and to prove if he has or not COVID. Another effort involving COVID-19 is trying to improve the time series propagation of COVID. We use the number of cases in each city reported by Johns Hopkins University, WHO, and we masked this with the open flights and open sky that report the flights around the world. We use this on the beginning of the disease, and with this information, we send it to a temporal neural network that try to estimate the propagation of the disease. So we use a set of 3 data sets, one for training, or other for validation, and other for test. Benefits of AI for healthcare. Well, deep learning has produced remarkable results for complex real-world problems that involve big data. It has the potential to provide data-driven, evidence-based clinical intelligence for advanced both biomedical research and service delivery. It's a new paradigm to derive insights on biological, diagnostic, and therapeutic processes and behaviors from data. It accelerates the process of digesting and interpreting vast quantities of complex and diverse information. But it has limitations. AI is not an all-purpose solution. For tasks that require common sense solutions or domain-specific expertise and situations that are outside the AI training data set, it is less applicable. AI has weakness. AI identifies superficial features and patterns, but lacks the understanding of meanings and concepts, lacks common sense reasoning, general intelligence, and domain knowledge integration, needs big data. Machine learning models are as good as the training data because the data has biases, noises, errors, and with AI, it's difficult to generalize the findings beyond its training data set. This is a big problem in AI. If you have a model, a successful model in a special data set, you can't, in many times, send these results to different data sets. So this is a problem in AI today. Limitations of AI for COVID-19 outbreak screening. AI technologies have penetrated in our daily lives with many successes. They have also contributed to helping humans in the extremely tough fighting against COVID-19, as we presented before. AI apps range from medical image diagnosis, chest X-rays and CT, virus transmission modeling, and forecasting based on a number of cases, time series data, text mining, and NLP. Although various studies have been published, we observe that there are still relatively limited applications and contributions of AI in this battle. This is partly due to the limited availability of annotated data, good data, that COVID-19 and AI methods normally require large amounts of data for computational models to learn and acquire knowledge. So here is some main reference that we use in this presentation. And thank you very much.
Thank you so much, Marco. The Q&A is open and so just reminding everyone, please use the Q&A option in the bottom of the screen as opposed to the chat box for questions. There is one from Megan Bichelle. There was a recent report in PNAS detailing poor CXR interpretation performance for CNNs trained on gender imbalanced training data. Have you been putting in any measures to balance the training data by gender or other patient characteristics?
No, we didn't. We did the balance between patients with COVID-19 and non-COVID. But we didn't did a balance according to the age or gender. We didn't this.
But are you planning to do that, Marco? That's part of the question.
Maybe, but our problem today is to have a number of cases enough to calibrate the network. This is not only our problem, but any research in this area has the same problem. But maybe age and gender could be another feature, important feature that is not in the image. It's outside, of course, the image. You need to collect this from the HR and put this on the model.
Yeah, thank you. So I have a question in a different channel here. So here we are tracking COVID data, and this is from Peter Amby from the Regenstrief Institute, testing and hospitalization data. So we are using testing and hospitalization data. Can you say more about how you're envisioning tracking of COVID using AI and other informatics capabilities in Brazil?
We start the first part of the question. We are starting this right now in our institute. We are testing all people here and crossing the results of the tests with our model to calibrate it and to improve the model. The second part of the question, I think for COVID, we are in the middle of the spread here in Brazil. Of course, for this disease, when we receive enough data, the disease disappeared. So we are working in our model to permit other kinds of disease outbreaks in years to come. But the main problem now is the volume of data that we have and data that is annotated with equality. In image or in reports, this is the big problem. If you don't have enough data, convolutional neural network is not a good tool. You need a lot of data to have quality with the network.
Yeah, I think Marco alluded to inconsistency in the government policies about releasing data. And so that makes it difficult to have a homogeneous data set. There is another question here from Vladimir Turzitsky, sorry for pronunciation. Have you explored using transfer learning to help deal with small data sets in chest X-ray COVID patients?
Yes, we did in our study using chest X-ray. As you could see, the data set that we used has no enough images. So we used transfer learning from another data set in terms that the initial guess of the weights comes from the transfer learning. So the answer is yes, we did.
There is another question. Was the meta-analysis of symptoms and conditions study published? What were the estimated risks you found?
In the meta-analysis, they didn't propose a risk factor. The meta-analysis just presented the dispersion of symptoms on a population of 50,000 people spread around the world. With these statistics, we decided to calibrate our model that produced the risk. In one of, I will return to a slide to complement my answer.
So is it published, Marco? That was part of the question.
Is in preprint.
Okay.
But just to finish, as you can see in this chart, the transition between H1N1 to COVID is very narrow. So the symptoms of a patient with H1N1 is very similar of a patient with COVID-19 moderate. So this is why we decided to put the risk factor.
There is another question from Eneida Mendonca. Is detecting COVID from X-ray really useful? Is this easier than conducting an antibody test or regular diagnostic test?
Depends. If you have the regular diagnosis test, you can, of course, obtain better result. Here is a screening. In our case, we are using chest X-ray because it's very easy to have this image.
So the other question is pretty generic, but maybe you can tackle that in a couple of examples. How much data is considered enough data?
That's a good question. Depends of your problem. In our case, when we are dealing with images, you need to have more than 1,000 images to have success. But of course, depends of the problem. Depends of the feature that you are looking for in the image.
Yeah. All right. So, Marco, I think that, oh, there is another one from the audience here, from Linda Hoxima. Has anyone looked at using AI to track the progression of COVID in the CXR over time? Hospital ICUs often do up to daily CXRs on some of those patients. It would be interesting to see if certain patterns in the progression predict how severe the disease is becoming. You lack the accessibility to data, and CXRs highlight the issue and interoperability and transfer of data. So multiple questions. I can repeat parts if you need.
It's a very long question, but we started this with our model to follow up and with a follow-up day by day with all people at the hospital here. So you can now we have a temporal series that we are studying and trying to get another indicator or another index that reports the severity of the disease in our team. So I don't know if I answered the question, but I think this is the next stage.
So, and your aim is to track a risk of severity or worsening of the cases?
Yes, yes. In fact, we are we starting this checking the number of people per day that has the risk above 3 in our case. So if this number per day improves, maybe the disease is going worse in our group.
So you're tracking the risk factor that you created in time also?
Yes, because all people here at the Institute receive a SMS message every day to update your conditions on our system. We calculate the risk score for that people and send it back to the employee. If the score is above 3, a message is sent to him or her to go to the physician. And at the physician, we collect or test the people and cross the data with the lab result.
So you're saying that you're using that risk metric both for staff and for patients?
Yeah, just for staff, not for patient.
Oh, okay. All right. So, so there is another question on lack of accessibility to data and CXRs. It's part of that big, larger question. Highlight the issue of interoperability and transfer of data. And I know you have an integrated system. Maybe you can talk a little bit about how that integration helps in getting both phenotypes and images and everything else?
Well, because it's not an integration, it's just one system. It's a AGR with a PACS system together. So we have access to the images, to the reports, to the diagnosis. So we have information from different dimensions at the same time. So this makes more easier to collect the data and put it all together in the same basket and analyze the data.
Thank you. There is a comment here for people that want to check, looking at technology that is not intrusive into privacy to do contact tracing in a more effective and consistent manner. Do you have anything in contact tracing going on, Marco?
In terms of contact tracing, just with the staff to participate in this collection of data, the staff respond a term. He agreed to share just your cell phone number, just this. So the risk factor is returned to this phone number. There is no name or other kind of information.
And they fill the information directly in a form or something?
Yes. Yeah, he agreed to participate in the collect of the data.
And you're collecting the data directly from the sensors on the phone, or they are typed by the person?
They are typed in a graphic form, so there is no insertion by the keyboard.
Okay, sounds good. I don't have any other question in the queue here. So, well, I'm gonna open the break. I think we will resume at 12:15. 12:30.
Yes.
So we'll resume our work with our panel at 12:30. I will thank Marco so much for his presentation today to us. One of the questions that I didn't pass yet is are the slides going to be shared for people that want to have them, Marco?
Okay, for sure, it's public.
Okay, so we'll figure out how to communicate the availability of the presentation materials. Stay tuned.
Just as a note to everyone, all 3 of the videos from the conference will be put up on Regenstrief's website by the end of the week. We should have links sent out to everyone who registered, so you should have those either tomorrow or Friday. Yeah,
sounds good. So I thank again Marco for it's an excellent work those guys are doing there. I have a particular interest in that because that was my home base for many years, and I'm so glad to see this effort to produce something valuable in places where the conditions are so adverse, and you can still produce high-end science and high-end technologies. It's all in the brain, and soon it will be in the machines and the brains of the machines of the humans and the humans and the machines. So thank you so much. We'll reconvene in 21 minutes. And I'm very excited about our upcoming panel. Stay tuned, enjoy your break, and see you soon.